Hello everyone, this is Murat Ozdemir. Today I will be talking about the fracture simulation of viscoelastic membranes by ordinary state-based peridynamics. Here is the outline of my presentation. First, I will be talking about the definition of viscoelasticity and its implementation in the numerical codes. Afterwards, I will be touching upon the ordinary state-based peridynamics formulation for viscoelastic materials. When we completed the formulation part, we can proceed for the verification of the proposed peridynamic formulation. I will verify my proposed formulation by the simple tension specimens of the viscoelastic membranes. Once the verification is completed, we can proceed for correct propagation simulations in viscoelastic membranes. I will finalize my presentation by the concluding remarks. So, what is viscoelasticity? Viscoelasticity is simply defined as the combination of elastic and viscous behavior. Elastic part of the formation is related to energy storage, while viscous part of the formation is responsible for dissipation of distortional energy. The elastic part of the formation is represented by spring elements, while the dashpot elements are used for viscous deformation. The material response of viscoelastic material is time dependent. As you can see on the left side, the material continues to deform under a constant loading. This phenomenon is also called as creep. At the same time, if a material is under a constant deformation, the material becomes to relax and the reaction force or the stresses decline gradually with respect to time. Numerical representation of viscoelastic properties. So we know how can we estimate or how can we model the viscoelastic materials, but we need to implement these representation in the numerical codes. The most common method to implement the viscoelastic materials is the generalized Maxwell model. In generalized Maxwell model, we simply connect Maxwell elements, a series of Maxwell elements with a spring element. In the generalized Maxwell model, mu's or mu represent elastic constant, while the viscosity of each Maxwell element is represented by eta. In the generalized Maxwell model, the relaxation of shear modulus is represented by Prony series. In this Prony series expression, alphas are related to elastic constants, or mu. Tau is related to tau is defined as the relaxation time for each Maxwell element and can be expressed as the ratio of viscosity to elastic constant of the associated Maxwell element. Here is the fundamentals of ordinary state-based peridynamic formulation. We define ordinary state-based formulation in undeformed and deformed states. In the undeformed state, x represents the position vector of each particle. For each particle, we define a neighborhood or horizon. The horizon radius is shown by delta. In each horizon, we define peridynamic interactions between the particles. As for the deformed state, we define the position of materials in the deformed state by y's. The displacement from undeformed to deformed state are represented by u. Then, in the peridynamics, we also define force density vectors, as you can see here, Tkj and Tjk. As you can see here, these force density vectors are aligned with the bond vector between the particles J and K. Actually, in peridynamics, we solve equation of motion. Here, you can see the discrete form of equation of motion for the particles in the peridynamic domain. The Tki and Tjk are defined along the bond vectors, as I mentioned before. Then we can express the force density vectors by the multiplication of force density and the unit vector along the deformed bonds. This expression represents the unit vector. We can also decompose the force density vector into dilatational and distortional parts. T kappa represents the dilatational part of force density vector, and Td represents the distortional part of force density vector. So in case of viscoelastic deformation, we keep the dilatational part of force density vector as the same with the linear elastic materials. This is the dilatational part of force density component. This expression is same regardless of the material type, either the viscoelastic material or linear elastic material. However, we need to revise the distortional force density component. As you can see here, there are some extension terms with the viscous deformation. E vis represent the viscous deformation for each Maxwell element in the Prony series. So I have briefly described the ordinary state-based peridynamic formulation. Now we can proceed for the verification of our formula. As for the verification purpose, I consider simple viscoelastic membrane under uniform tension. The tension stress is 2000 Pascal, and the main dimensions are given here along with the basic or main material properties, including elastic modulus and the density of the material. On the bottom, I have given the analysis procedure, loading time and total simulation time, along with the time increment size and the finite element modeling procedure. On the table given in this table given on the right hand side, I have described the viscoelastic parameters. This column, tau column, represents the relaxation time for each Maxwell element, whereas the column on the right side, E column, represents the elastic constants for each Maxwell element as well as the single spring element at the bottom. If we would like to calculate the elastic constant or elastic modulus of the generalized Maxwell model when the time is equal to 0, we simply need to summate all the terms in this column. When we perform time-dependent or transient analysis with finite element and ordinary state-based peridynamic, we can capture the creep deformation first. This part represents the creep deformation. The membrane continues to deform under constant loading, and we remove loading at this point. Then, beyond this point, we can capture the recovery of the material. In both sections, the creep and recovery section of the deformation, our peridynamic code is able to capture deformation very well. Since we have verified our ordinary state-based peridynamic code, we can proceed for crack propagation simulations. As you can see here, I have introduced a central angular crack. This crack has an angle of 45 degrees with respect to the horizontal axis. Load magnitude has been changed. I have defined this load magnitude so that the crack propagation doesn't take place at the beginning, but as the time passes, we can observe crack propagation since the relaxation of the material or the time-dependent material property. Here you can see the discretized peridynamic model of the cracked membrane. As for the crack propagation rule, I have considered critical bond strain energy density. This criterion states that uh, if the strain energy density stored in a bond exceeds this critical value, the bond is broken irreversibly. When we perform transient crack propagation analysis, we can observe the crack propagation. This is the snapshot at the time of 1 millisecond, and 2 milliseconds, and 5.2 milliseconds. At this point, if you notice the tip of cracks, there are signs of crack propagation. So we can expect crack to propagate soon. And when the time hits 5.3 milliseconds, we can observe the full failure of the membrane. Here are the conclusions of my presentation. Firstly, we have talked about the viscoelastic constitutive model and its implementation in peridynamic and finite element method. We used Prony series in the viscoelastic material models. We were able to capture both creep and recovery behaviors by FEM and ordinary state-based peridynamics. As a short case study, we considered one single crack propagation case. The angular central crack didn't propagate up to 5 milliseconds. The full failure took place at 5.3 milliseconds. As a future work, we can study failure of membranes under operational loads, I mean the biaxial tension loads, by using peridynamics. Of my presentation. Thank you very much.